So we've looked at the, I guess, the theoretical side of arithmetic and geometric series. So how can we apply this to word problems? I got to admit, some of these HSC questions, they're a little bit forced. You know, are they really realistic? I mean, have a look at this one from 2007. Heather decides she's going to improve her fitness level. Now, I don't know how many of you are swimmers. On day one, she swims 750 metres. Not happening. If you're not a swimmer and you go, you know what, I might take up swimming and to improve my fitness level, I think just to start off with, I'll do 15 laps. It doesn't happen. And then, even more ambitiously, and saying, you know what, I'm going to add 100 metres to that every single day. So, and just in case we can't work out what that means, they explain it for us. That means she swims 850 metres on the second day, 950 on the third, and so on. So lovely, we get an arithmetic series. So what they want to know is, okay, well, because we now know it's an arithmetic series, let's find out a formula for how many metres that she'll swim on the, or if you read that, on the nth day. Okay. It's a matter of extracting the relevant data from the question. We've identified its arithmetic. The first term, yes, day one, ambitiously 750 metres. And every day we're going to improve that by 100, so that will become our common difference. And now we can just do the math. So a plus n minus 1d is our general term, subbing it in, and we get a formula for the nth day. Now that we've worked out a formula, we can work out on any particular day how far she's going to swim. So how about the 10th day? And it's now just same as all our normal arithmetic sequence questions. Let's sub into our formula. 1,650 metres on the 10th day. Remember, the longest Olympic swimming event is 1,500 metres in the pool. Okay, I suppose they do longer ones in the open water. So in those 10 days, how far has she swum altogether? Oh, that would be a sum to 10. So using our sum formula, so subbing in our info, and what have we got? 12,000 metres, or 12 kilometres we could say. I did do the other way as well, because we do know our last term. Sure enough, we get the same answer, depending on which formula we use. So 12,000 metres. And of course, something that you'd obviously want to know. After how many days is the total distance she swum equal to the width of the English Channel? That's one of those big challenges in swimming, to swim the English Channel. Mind you, I don't think they do it by going 150 metres. No, what was it? 750 metres the first day. Oh, we'll just stop. Right, now we'll go to the next. I think they do it all in one hit when they try and swim the English Channel. So 34 kilometres, which of course is 34,000 metres. So sub that in for our sum to n. We want to find out what n is. We end up eventually, move the term over, there we go. We end up with a quadratic. So what multiplies together to give negative 680 adds together to give 14. Oh, of course. 20 and negative 34, there we go. So our solutions, n is negative 34, n equals 20. So foolishly, it took her 20 days. This one quite possibly is a more realistic application. Companies looking at their sales, they notice they're declining by 6% every year, and they had 50,000 items sold in the first year, 2001 there. So when they're trying to predict if it continues going at 6% every year, when will sales fall below 20,000? Now, I guess this is far more realistic, and people do use these sorts of things because they say, well, let's assume it is a pattern, and they try to predict when things are going to happen so they can plan accordingly. So, all right, first term is 50,000. This one's going to be geometric because we're going down by 6%. Remember, the ratio is not 6%. The ratio would be 94% or 0.94 because we're declining by 6%. So we want to know when is the first time the general term is less than 20,000. Yeah, 20,000. So AR to the n minus 1. So when is 20,000? Oh, I've just reversed the sign there. So greater than 50,000. We have an exponential to solve, so we'll log both sides and bring the power to the front. Now I'm dividing by the log of 0.94. So I'm going to have to change the sign, because remember, anything log of something smaller than 1 is a negative number. So log of 0.94 is actually negative. So I've changed it to a greater than sign. And we get n minus 1 is greater than 14.8, etc., etc. So therefore n is greater. We want the first... Oh, hang on. Do I want the first one greater? The question is, during which year? It's going to happen at around about 15.8. So it would be during the 16th year, wouldn't it? This would be one, I guess, if it was a rounding question, we'd always round down, wouldn't we? No, round up. So even if it was 15.1, we'd round up, wouldn't we? Yeah. So sometimes we have to think about that, about the logic of the question, rather than the normal rules of rounding and what have you. So the 16th year, which would be 2016, that's their prediction. That's when sales will fall below 20,000. Let's have a look at another HSC one. Yeah, I guess it's sort of realistic, this one. So Anne and Kay are both employed by an accounting firm, but they accept different conditions of employment. Anne accepts employment, initial salary 50,000, and then says every year the salary is going to increase by 2,500. That's probably unrealistic. That doesn't normally happen, where they just say it's a fixed amount that it's going to increase every year. The second one is possibly a bit more realistic, where Kay says, yeah, I'll start at 50,000, but I want a 4% increase each year. That's probably more a realistic sort of condition. But conveniently, weird how it worked out, Anne has accepted an arithmetic sequence, whereas Kay has accepted a geometric sequence. So the arithmetic one, first term is 50,000. Common difference, we're going up by 2.5 each time. The geometric one, also 50,000 for the first term, increased by 4%, so the ratio is 1.04. So the question is for Anne's salary. So Anne was the left. Put it into our general term. We want term 13. So 80,000 would be in her 13th year. Well, how well did Kay go? Did she do better or worse than that? So now it's AR to the n minus 1. Her salary, $80,051. Not to forget the 61 cents. Oh, maybe they'll even give us 62 if they're feeling generous, because it is 0.093 there. So after 20 years, Kay obviously is going to end up with more money than Anne. But how much they want to know? How much after 20 years? So we now want to find the sum. So for Anne, hers is arithmetic. Subbing in, we get $1,475,000 after 10 years. Sorry, 20 years. I just wrote 10 there. I was going to say, after 10 years, that's not bad. 20 years is a bit more, yeah, that's a bit more realistic, I think. K, sum to 20. $1,488,903. So it's actually not that much more, but it is significant, not significant. Well, I don't know. Would you call it significantly more? Almost $14,000. I suppose that is significantly more. Here's a quick little one from 2007. Find the limiting sum. Find the limiting sum. So sum to infinity. So first term's 3/4. The ratio is 1/4. So sum to infinity. Eventually, it's 1. All of that adds up to be 1. In 2003. Interesting, you look at the placement. This was before multiple choice. So 1 was right at the start of the paper, going to be a real easy question. Whereas this limiting sum question is in question 7. Now, this is a 2-unit paper, but they're obviously considering this to be a much harder question than the one above, when really they're identical questions. If you look at it, it's just the second one has those evil surds in them. But that's why I guess they've said this is a harder question than the first one. But we do exactly the same, of course. Fine, the first term is 2. The ratio is 1 on the square root of 2 plus 1. Why I did all that work, I don't know, because it's kind of obvious. I've multiplied by 1 on the square root of 2 plus 1, but there you go. Sum to infinity, a on 1 minus r. Yeah, I suppose there's a bit more work than the other question, isn't there? So we've got 2 over 1 minus 1 on the square root of 2 plus 1. Playing around with that, eventually it comes down to, there we go, 2 plus root 2. 2 plus root 2. Here's one that does not, and it's explain why. So it's the part 2 of that question. Explain why this particular one does not have a limiting sum. Well, that's where they're looking for the idea about the ratio being in between minus 1 and 1. And so the ratio is 1 on the square root of 2 minus 1, which is bigger than 1. Bigger than 1, so no good. Look at the placement this time. Back when there was no multiple choice, there were 10 questions in the tuna paper. So they've placed this one at 9. So now they've thrown trig in it. So consider the series 1 minus tan squared plus tan to the power of 4. So a is 1. My ratio is negative tan squared. So the question is, when it does exist, because there's, for some values of theta, there will be a limiting sum, and for other values of theta, there won't. So they're just saying, okay, let's assume, we're just working with the ones where it does exist. Find what its value would be. So a on 1 minus r. I suppose mere mortals might have left it like that, but we would have looked at it and said, ha ha ha. 1 plus tan squared is, of course, and then the reciprocal of sec is cos. So our sum to infinity is cos squared theta. Now, it's saying, well, okay, we know it's not always going to exist, because there'll be some values for tan theta where that ratio will end up being bigger than 1. So they want to know for what values of theta. We're just looking at one piece of the tan curve, so going from minus 90 or pi on 2 to plus 90. So just one piece of the tan curve. So we know we want to trap the tan curve in between minus 1 and 1, those y values. So minus tan squared was our ratio. That's going to go in between minus 1 and 1. Well, I'll multiply everything by negative 1 to get rid of the negative sign, but that means my inequality signs change around. But I actually end up with exactly the same inequality. Because if I was to rewrite that, I now get tan squareds in between minus 1 and 1. Alright, that means tan must also be in between minus 1 and 1. Because if I'm going to square a number and get an answer between minus 1 and 1, I suppose reality is it's going to be between 0 and 1. You can't square and get a negative number. But if I'm going to square a number and get something between 0 and 1, then that number must be between 0 and 1. Because I mean, if you square a number bigger than 1, it's going to get bigger. So I know tan goes in between minus 1 and 1. Now, we also know tan of 45 is 1. That's one of our exact values, or pi on 4. I think it's easy if I now just look at the graph and see what we're saying. So there's the piece of the curve. We're basically saying, for what x values is this curve going between y values of 1 and minus 1? Okay. Those x values would be 45 degrees, or pi on 4. Pardon my scale, because it should be in the middle there, shouldn't it? So we know then the theta, we want the ones in between minus pi on 4 and pi on 4. So yes, that certainly was a bit more involved than a standard limiting sum question. We can see why they placed that one at number 9. Okay, So, exercise 7A, I think that one's in the second book, or the Year 12 book, the green book.